Okay, we start recording already, so we will start our lectures today. See, okay. You can see the orange frame happen. Okay, stop sharing first, then share it again. Okay, so today we are going to talk about the combustions of the fuels, right, which is the main source of energies for our internal combustion engine, right? Combustion of the fuel, because it will create the heat, okay, for us. Okay, so combustions of fuels can be accomplished by mixing the fuel with the air, right, at a high temperatures, right? So when we have fuels and air, right, both of these at the high temperature or elevated temperatures, right, the reaction will happen, and that means we will have the product of combustions and also the heat that come out, right? And this heat will convert into work for us. Okay, so why this reaction happen, right? Because we have oxygens, right? The oxygen that contained in the air, right, will unite chemically or react chemically with the carbons, hydrogens, and also other elements in the fuel that we mix with the air, right? So it produces the heat, right? And what is the amount of heat that come out? How much that the heat come out? The amount of heat that come out liberated during the combustion process, right? It will depend on how much that we can do the oxidation or how much that we can oxidize the amounts of fuel compositions, right? And also the characteristic of the fuel itself, right? Because the fuel from different sources, right, they will have different components, right, or different elements for that fuel. Okay, of course, we would like to have a high efficiency combustions, right, when we do the combustions. So the high efficiency combustion require what? First, we need to have sufficient amount of the air that's supplied to the combustions, right? The amount of the air have to be enough, right, when compared with the amount of the fuel, right? So good combustion can happen, right? The second thing is the air and the fuel, right, that we bring two of this into our combustions. It have to be mixed thoroughly, or homogeneity might have to be happen. Okay, the homogeneity between the fuel and air, when it become a mixture, it have to be happen. Okay, number three, the temperature have to be high, right? The temperature of the mixtures, right, have to be high, right, in order to ignite the mixtures, right? And the last one is very important. Apart from all the three that we mentioned, right, we need time. Combustion need time, right? Because if you remember, right, when we ignite the mixtures in during compressions process, right, the combustion does not happen immediately. The combustion need a little bit of delay in time after ignition happen, right? And when it happens, it needs time for the combustions in order to burn all the fuels or all the mixture that we send into the chambers completely, right? So we need the sufficient time for the combustion, right, in order to finish everything, right? Burn everything completely. Okay, so this is how we can make the high efficiency combustions. The amount of the air, the homogeneity of the mixture, the temperatures, and the time. Okay, so let's get into the combustion process. Anything that we put into the combustion first, right, before it go into the combustions, we call that the reactants, right? So the initial substances that undergo the combustions are all called reactants. And anything that come out from the combustions, right, after combustion finish, right, everything that come out, we call it the products. We call it the products. So if you look at this, some example of the combustion process, we have methane, which is CH4, right? And then we have air. This is the amount of air, right? In terms of air, we will look at oxygen, nitrogen, and sometimes we look at the amount of the water vapor in the air. It depends. Okay, but mostly, right, when we perform the combustion analysis, we will look at the air as oxygens and nitrogens, right? And every mole of oxygens, right, we need 3.76 mole of nitrogen. How this 3.76 mole come out, right? It come out because we know that if we do the analysis of the air, right, and we do it based on the volume basis, we found out that in the air we have 71% of the oxygens by volume, and we have 79% of nitrogen by volume. Right? This is done on the volume basis when we do the analysis of the air. We can also do by mass basis, also or mole basis, right? But for mole basis, the result gonna be the same as on the volume basis. Right? So since we have 79% of the nitrogen and 21% of the oxygen, so if we put 79 divided by 21, the number gonna be 3.76 show right here, right? So that means every moles, right, or every volume of oxygens will have 3.76 volume of nitrogen. In terms of mole, every mole for oxygen will have 3.76 mole of nitrogen in the air, right? So this represents the air here, right? How about the number 2 in front here, right? It will come out after we what? After we do the balancing of the atom or mole on both sides of the combustion, not more on the atom of the element on both sides of the combustions. Okay. On the right hand side here, these are the products. We have CO2, we have water, and we have nitrogen come out, right? Okay. If we have only these 3 products, it means we have complete combustions, right? So when we talk about complete combustions, the products will refer to only CO2, water, and nitrogen, right? No other products apart from this come out, right? Whenever we talk about complete combustions, right? But if it's not complete combustion, then we have other elements or other products come out on the right hand side. Okay, again, the number here, 2 and 2 here, right, is come out from balancing of the combustion equation or the combustion reactions here. Okay, so this is the examples of the combustion process. Right? This side we call is the reactant, this side we call is the products. Okay, so let's do the analysis, right, on the combustion process. Right? So in most engineering combustion system, right, the necessary amount of the oxygen, right, that need to react with the fuel come out from air, right? We need the air, right, in order to get the amount of oxygen, right? And this amount of the oxygen have to be mixed with the fuels, right? So most of the engineering combustion, we bring the air in order to get the oxygen, except when we talk about the rocket, right? In the rocket, right, what they bring is just only oxygen, right? They only bring oxygen tanks and the fuel tanks, right, into the rocket. Right? So when it mixed together, it's gonna be the mix between oxygen and fuels only. Okay. So since we bring the air into our combustions, so it is necessary to use the accurate and consistent analysis of the air by mass and by mole and or by volume, right? That I just talked about, right? And in the combustion calculations, right? In terms of mass, right? Air is taken as what? Right? When we do the analysis on the mass basis, we will have 23.3% of oxygen, right? And 76.7% of nitrogen. Right? In terms of volume, right? We will have 21% of oxygen and 79% of nitrogen, right? So since we bring the air in our combustions, right? So not only oxygen that we have to take a look in the combustions, right? Since air contains oxygen and nitrogen, right? So we have to take nitrogen into our combustion equation as well, right? Even though we know that nitrogen is the inert gas, right? But we do have to take the nitrogen into our combustions, right? So in the analysis, as we already mentioned, right, 1 mole of oxygen will go along with 3.76 mole of nitrogen, and this will represent the air, right? And in fact, everybody know that the air is not dry, right? The air always contain moistures or humidity, right? And this amount of moisture and humidity is very over wide limit. So it means over wide range, right? It depends on the meteorological conditions, right? Or in other words, depend on the weather conditions, right? That is how much is the moisture or humidity that is in the air, right? We can know the amount of moisture or the humidity in the air by using what? Any student know? In order to get the amount of moisture and humidity in the air, right? We can use what kind of chart that we can use? What kind of chart that we can use? You learned it in thermodynamics, right? In the mixtures chapters. What chart that we can use in order to get the amount of moisture and humidity? Any student know? The chart that we use is the psychometric chart, right? on the psychometric charts, we know everything about the air, right? Because that the life of the air, right? Everything that we plot on the psychometric chart represent the life of the air. Right? What is the temperature, the dry bulb temperature, the wet bulb temperature, the humidity ratio, the relative humidity, the enthalpy, even the water vapors in some chart, right? It also show the water vapor of the air inside the air. Okay. Since the amount of moisture and humidity vary, right? So in most cases, in order to simplify the combustion analysis, right, we just look at the moisture or humidity as an additional amount of the inert material. That means look at it the same as nitrogen, right? In order to simplify our analysis, or in other words, right, we neglect the amount of moisture or humidity in the air, and that's the reason why when we do the combustions, right, you seldom see the amount of the water as a reactant here, right? Because we want to simplify it, right, so that we can do the analysis easier. Okay, so that is the combustion process. Okay, now let's look at the calculations, right? In terms of calculations, we have to do the balancing first. This is a must, right? This is a must, right? Anything that you do with combustions, right? The first thing, always the first, is to balance the combustion equation or the combustion process, right? So if we have a complete combustion, right, because we have only CO2, water, and nitrogen in here, right? So this is a typical complete combustion equation, or the stoichiometric combustion, in which we have fuel, any fuel represented by CXHY, plus the stoichiometric coefficients. Again, this we have to find from what? Balancing. And the dry air and the product of combustion here, right? So in here, since our internal combustion engine use only what? The liquid fuels or the gas fuel, right? We seldom use the solid fuel such as coal, right? Such as coal, right? So that make us a little bit easier in doing the combustion equation, because when you talk about the fuels, right, that is liquid or gas, right, mostly it will contain only carbon and hydrogens, right? Nothing else. It's not like a coal, right? That sometimes apart from carbon, apart from hydrogen, it contains some other elements as well, right? For example, it may contain water inside the coal, right? Because it's a humid coal, right? It may contain oxygen in the coal, right? It may contain sulfur in the coal, right? So that means when we do the combustion analysis, we have to put all of this on the left-hand side, because we burn coal, right? So every component or every element in the coal have to be burned as well, right? So it makes the analysis more complicated, right? Because on the right-hand side here, it will never have only CO2, water, and nitrogen. It will have some other element come out, right? Because as I mentioned, you have oxygen in the coal, right? You have water in the coal, you have sulfur in the coal, right? So all this have to react, right? And it will come out into the product of combustion. Okay, but for us, we only have hydrocarbon here because we deal with liquid fuel and gas fuel in our internal combustion engine. Okay, so we have to do the balancing, right? The balancing is done on the conservations of all atoms, right? Of all atoms here on the left hand side and the right hand side, right? The stoichiometric amounts of the air, right, that come out from stoichiometric combustions, right? Or in other words, we can call it the theoretical amount of the air, right? It is the minimum amount of the air that will supply sufficient oxygen for the complete combustions, right? So when we talk about the theoretical amount of the air or the stoichiometric amount of the air, is always referred to the minimum amount of the air, right? The minimum amount of the air. So sometimes, right, in some example, they may ask you to find the minimum amount of the air, right? Instead of saying find the stoichiometric or theoretical amount of the air, they say find the minimum amount of the air, right? And that means you have to do the stoichiometric combustion first, right, in order to come up with the stoichiometric amount or theoretical amount of the air, right? So, but anyways, right, anyway, in the actual combustion process, right, when we encounter in practical combustion process, right, it is a common practice to use more air than the stoichiometric amount. Right? So don't be surprised when you go out, right, to the factories and you find out that they use more amount of the air than the theoretical amounts. That always happen. That's why they said it is a common practice to use more air than the stoichiometric amounts. Right? And this we call it the excess air. Right? So when we talk about the amount of the air that higher than the amount required from stoichiometric, it is called the excess air, right? And since we have the excess air, right, of course, in the opposite directions, right, any amount of air that is less than the stoichiometric amount, right, we will call it the deficiency of air, right? So we have the stoichiometric amount higher than stoichiometric amount and lower than stoichiometric amounts. Right? And in the internal combustion, if you remember, right, we have the stoichiometric ratios, right, where air fuel ratio is 14.7, right, and we also have lean mixtures, right, where the ratio is higher than 14.7. We also have rich mixtures where the ratio is less than 14.7, right? So we have more amount of the stoichiometric and also less amount of the stoichiometrics happen in our internal combustion engine. Okay, so since we have air and fuel, right? The air fuel ratios, right? We can have this term in both on the mass basis or on the mole basis. Right? If it's on the mole basis, it's gonna be very simple because if we finish our combustion equations, we do the balancing already, we can come up with the air fuel ratio right away, right? If we want to show it in terms of the mole basis, because it's the number of mole of the air divided by the number of the mole of the fuel here, right? But in terms of mass basis, then we have to change from mole to mass, right? By using this equation, right? Mass is equal to mole times the molecular mass. Okay, so the molecular mass of the air is equal to what? 20x, right? And you have to find the molecular mass of the fuels, right? Because the and it's a little bit difficult because our fuel is always a compound, right? For example, it have carbon, it have hydrogens, right? So you have to find these two mass all together by using these equations, not only one, right? We write it down here fuel, but we know that our fuel is the hydrocarbon compound, right? So it have carbon, it have hydrogens, right? So we have to sum the mass of the carbon and the mass of the hydrogen all together. And the mass of the carbon and mass of hydrogen can be found from here, right? This equation. Okay, we also have the fuel air equivalent ratios. The fuel air equivalent ratio. This is the term that we know that our mixture is lean or it is rich or it is stoichiometric, because this fuel air equivalent ratio, right, is the ratio of the actual fuel air ratio, right? Remember, if we put F in front of A, it means we talk about fuel air ratio, right? Not air fuel ratio like this, where we put A before F, right? So the fuel air equivalent ratio is the actual fuel air ratio divided by the stoichiometric fuel air ratio, right? So if we want to put air in front, right? So the fuel air equivalent ratio will be the air fuel ratio of the stoichiometric divided by the air fuel ratio of the actual one, right? So since it's compared with the stoichiometric, right? So we will know that if this fuel air equivalent ratio is equal to 1, then it's gonna be what? Stoichiometric, right? And if it's less than 1, it's gonna be lean mixtures, right? If it's greater than 1, it's gonna be what? If it's greater than 1, it's gonna be rich mixtures, right? Greater than 1, that means this amount is less than this, right? The actual air fuel ratio is less than this. So since actual air fuel ratio is less than the stoichiometric amount, so it's gonna be rich mixtures. Okay. We have also another term called the relative air fuel ratio, right? Using lambda, it is 1/3 or 1/fuel air equivalent ratio, right? So it depends, right? Who prefer to use what parameters, right, in order to know right away that the mixture is lean or the mixture is rich. Okay. So if this phi is equal to 1, right, it is a stoichiometric. If it's less than 1, it's going to be a lean or weak mixtures, right? And if it's greater than 1, it's going to be a rich mixtures here. Okay. So that is the balancing, right? We do the balancing of the combustion equation first, and this is the thing that we have to do it first, always. Okay. So after combustion happens, right, we have the product of combustions, right? This is we call it the product of combustions, but outside know it in other name, right? Exhaust gas they call, or sometimes they call it a flue gas, right? So exhaust, flue gas, they are products of combustion, right? So we have to do the analysis on the products, right? Not only the analysis on the fuels, we also have to do the analysis on the products. Why? Because from the products that come out, we can know that the combustion that happened is good or is bad, right? And to do the analysis, right, on the product, it is usually done by volume or by mole, right? They're the same thing. By volume, by mole, result is the same. Okay, so we have two ways to do the product analysis. The first one is dry product analysis. Right? To do the dry product analysis, we will let the exhaust or the flue gas that come out. Right? We let it cool down to the temperatures below the saturated temperature of the water vapor. Right? Because if we let the temperature below the saturated temperature of the water vapor that also come out in the flue gas or in the exhaust, right? That water vapor will condense, right? It will be condensed if the temperature of the exhaust or the flue gas, right, go down below the saturated temperature of the water vapor. Okay, so it needs time. It needs time when we do the dry product analysis because we have to wait until the water vapor condense, right? So there is no water, right, in our products. But for wet product analysis, right, we can do it immediately, right? After we take the exhaust sample or the flue gas sample, right? We can do the analysis immediately or right away, right? Because we don't care that the water vapor is condensed or not condensed. Okay. So look at the examples, right? How we can do the dry products or the wet product analysis. Okay. Find the stoichiometric air-fuel ratio or the combustions of the ethyl alcohol, right? The ethyl alcohol is C2H5OH in a petrol engine, right? Or in the gasoline engine. And after we find the stoichiometric air-fuel ratio, they want us to do what? Calculate the actual air-fuel ratio, right? If they use 0.9 or and 1.2 equivalent ratio, that means they want us to perform the combustions, right, for the lean mixtures and the rich mixtures, right? And then after we perform the combustion under lean mixtures and lean mixture and rich mixture, then they want us to determine the wet and dry analysis, right, by volume of the exhaust gas that come out for each equivalent ratio. So imagine you do the combustions and then you do the product analysis. Okay, so let's first, right, we do for the stoichiometric first. Right, so we write down the combustion equations of the ethyl alcohol. Right, we have this ethyl alcohol, we have the amount of dry air, and this is the complete combustions. Right, so we do the balancings of all the atoms on the right hand side and the left hand side. Right, the left hand side and the right hand side. Okay, and we come up with the stoichiometric coefficients. So right here. Okay, so from this we have to lead the combustion equation now. After we finish, right, we have to be able to lead the information that show in our combustion equations. Right, so from our combustion equations, the first information that we get is under 1 mole of the fuels. Right, under 1 mole of the fuel. This is usually what we done for the combustion equations. Right, we will finish our combustion equation on the condition that it will show only 1 mole of the fuels, right? Because it's gonna help us in finding the air-fuel ratio, right? Because in the air fuel ratio is always talk about 1 mole or 1 kilogram of the fuel. So it's better to finish your combustion equation, right, with 1 mole of the fuel always. Okay, so 1 mole of the fuel, right, has a mass of what? We have 2 carbon here, right, and we have 1 oxygen here and 6 hydrogen altogether, right? So we use the molecular mass of the carbon, of the oxygens, and the hydrogen here, right? 12 represent the molecular mass of the carbon. Oxygen is 16, right? And hydrogen is 1. Right? So overall, for 1 mole of this ethyl alcohol, we have 46 kilograms of the ethyl alcohol that represent 1 mole of the fuels. Okay. The second information is the mass of the air required for the complete burning, right, of 1 mole of the fuel. Right. To burn 1 mole of the fuel, this is the amount of the air. Right. So what do we have? We have 2 oxygens, right? So the molecular mass of 2 oxygen is 32. Right. We have 2 nitrogen here, and the molecular mass of the 2 nitrogen is 28. Right. Times with the number of mole in front. So we come up with 412 kilograms of the air. Right. So 46 kilograms of the fuel require 412 kilograms of the air. Right. So on the mass basis, right, if we want to find the stoichiometric air fuel ratio on the mass basis, it's going to be what? The amount of the air 412 divided by the amount of the fuel 46. And the result is 8.96 per 1. Right? It's not 14.7. Correct? Because that 14.7 is on the volume basis or on the mole basis. Okay. So to check, right, we also do it on the volume or mole basis. Right. So the volumetric air fuel ratio or the stoichiometric air fuel ratio on the volume basis will be what? On the volume basis, we will have 3 mole, right? We have 3 here and 3 here. So it's 3 mole of the air, right? So we put 3 out. We have 1 oxygen here and 3.76 nitrogens. So the total number of mole will be what? 14.3. Compare with 1 mole of the fuel here. Right? So it's 14.3, right? Close to the stoichiometrics, right? 14.7, the general one. Okay, so with the stoichiometric ratio that we get, right? So if we go for free or lean mixtures, free equal to 0.9 lean mixture, right? So the actual air fuel ratio that we use for our lean mixtures will be what? 0.9 equal to 8.96, right, which is on the mass basis here. So the air fuel ratio, the actual one, will be what? 9.95 on the mass basis, right? So since we know the amount of the actual air fuel ratio on the mass basis, which is 9.91, right, then we can perform the wet and dry product analysis. That means we know the air fuel ratio of our mixture, right? Then we can do combustions, and after combustions, then we can do wet and dry product analysis, right? But first, with the air fuel ratio actual here, right, we need to find the actual amount of the air that's supplied. Right? What is the actual amount of the air that's supplied, right? So since it is the lean mixture, you expect that the amount of the air should be what? Higher than the amount of the stoichiometric, right? Okay, so It's very easy that how you gonna use this fee to come up with the actual amount of the air, right? So it is 1 over 0.9, which is 1.11 of the amount of the theoretical air, right? That means the actual air is greater than the theoretical air because you see it 1.11 here, right? So after we know that we have to use 1.11, right, amount of the air than the theoretical air, right? We're gonna bring this number into our combustion equation. We know the fuel, we know the air here, right? This is the theoretical air, correct? 3O oxygen plus 3 times 79 divided by 21. This is the amount of the theoretical air. We know that it is not a complete combustion. So we have CO2, we have water, and we have nitrogen. Right? So what is the result of the incomplete combustion? Show right here. How do we know this? At the beginning, we don't know, of course. Right? We don't know. We don't know that, hey, why oxygen happened at the beginning, at the very beginning. We don't know, right? But we can write down CO2, we can write down hydrogen and water, and we can write down nitrogen. We can write down the theoretical amount of the air here. Okay, first, and then we time it with 1.11. Okay, after that, then we do the balancing, right? And through the balancing of the combustion equation, then you will know that why this oxygen happened in our product of combustion. It not happen right away when you first write the combustion equations. Okay, right? So we do the stoichiometric first, and then for the lean mixture, we know that we have to use 1.11 of the amount of the air. So we time 1.11 here, right, with the theoretical amount of the air here. And then we do the balancings. And through the balancings, we know that there will be some amount of oxygen that left over in the products of combustions. Okay, so when we finish this, right, we calculate the total number of moles of the products, right, in which we have what? 2 mole of carbon dioxide, 3 mole of water, 0.33 mole of oxygen, and 12.54 mole of nitrogen. Right. Combine all of this mole together, we have 14.87 mole. This is the total number mole of the products. Right. So for wet product analysis, right, the result will show in terms of percentage on mole or volume basis for each product, right, in the total product. So that means what? We have 2 mole of carbon dioxide in the product. So it's 2 divided by 17.87 times 100. So that means in our product here, right, it consists of 11.20% of carbon dioxide. Right. The rest of the product, we perform the same. We do the same. Right. Right. After we finish all the products, right, that means we finish our wet product analysis. For dry product analysis, right, we just take the number of mole of the water out, because when we talk about dry product, there is no water, right? So the total number of mole of the dry product, right, will be less than the total number of mole for the wet product, right? Because we take water out, right? And the result is 14.87 here. And we do the same thing, right? Except we don't have water because it's already taken out, right? It's taken out in our analysis. Right? So we have only 3 elements or 3 products left over here. Okay, so for phi equal to 1.2, which is what? The rich mixtures, right? Rich mixture. So the actual air fuel ratio, right, have to be less than the stoichiometric. So if you understand about this, you don't need to remember the equations, right? This is where you can use your common sense. This is where you can use, okay? You don't need to remember what is the definition for phi, right? You just know that if it's less than 1, it's green. If it's greater than 1, it's rich. And making use of knowing lean and rich, right, to find the actual air fuel ratio, right? Okay, so the actual air fuel ratio have to be less than 8.96, right? And the result is 7.47, right? And again, the amount of the air supply, right, it have to be less, right? So it's 1 over 1.2, which is what? 0.834 for the theoretical amounts. And then you perform the same thing, right? In here, they show you how the combustion equations have been done, right? In order to finish the balancing, right? So they have fuel, they have the theoretical amount of the air, they time it with 0.834 in order to get the actual amount of the air. And on this side, they have CO2, they have water, they have nitrogens, right? How about this? Again, at the beginning, you don't know, right? You don't know that this carbon monoxide or any other thing else happen. Doesn't matter. Okay, you leave it, and then you perform the balancing, right? And form the balancing, then you know that it have to have this CO. Some students said, can I have carbon alone, or can I have oxygen alone? Okay. Some students might say, I can write down 1 carbon, 1 oxygen. Right? Unfortunately, 1 carbon may happen, but it will not involve in our products. Right? And 1 oxygen cannot happen because oxygen, right, under atmospheric pressure never be able to stand in just 1 atom, right? It have to be diatomic oxygens, right? So on this basis knowledge, then you know that this carbon and oxygen have to react with each other, right? And then create this carbon monoxide here, okay? So this is how you can come up, right, with the complete combustion equations. Okay, and again, after you complete finding all these coefficients here, right, we don't call this stoichiometric coefficients because it's not stoichiometric, right? So we just call it the coefficients. So after you get all the value of the coefficients, then you know the total number of mole for the product. And again, you do the wet product analysis, the same that we just mentioned before, and also the dry product analysis, same thing. Okay, any questions in the first example? Any questions? If not, then I go for the second example. A hydrocarbon fuels of a composition 84.1% by mass of the carbon and 15.9% by mass of the hydrogen, right? Have a molecular mass or weight of 114.15. Determine the number of mole of the air required for stoichiometric combustions and the number of mole of the products produced per mole of the fuel, and also calculate the air-fuel ratio stoichiometric, fuel-air ratio stoichiometrics, and the molecular mass of the reactants and the products. Okay, they give you the molecular mass of the air, carbon dioxide, water, nitrogen, oxygen, carbon, and hydrogen. Okay, now look at the examples. Do you know exactly about the fuel that used? Right? From the information that they give you, they do not say what kind of fuel, what is the fuel that they use in this combustion. Right? The information about the fuel that they give to you is only the compositions, right? Which is what? Carbon occupy 84.1% by mass in this fuel, and hydrogen occupy 15.9% by mass in this fuel. So you don't know what? You don't know the fuel. So how we can write down the combustion equation? Some student might ask, I don't know, I cannot write down. Right? So if I cannot write down the combustion equation, then this example, you done, right? You done. Only you think that I don't know what is the fuel. Okay. But if you say that, if you think that, even though I don't know what is the fuels, right? What the fuel it is, right? I keep going with the belief that I learned on combustion, right? So you go with your belief. You go with your belief. You don't know the fuel, doesn't matter. At least you know that it is carbon and hydrogen, right? So you have CXHY here. This is the unknown fuels, right? So you go with CXHY, you go with the air, right? You go with the complete combustions, CO2, water, and nitrogen. And then you perform the balancings the way that you used to do, right? In order to get all the stoichiometric coefficients. And this show you the results, right? Show you the result in which we can call it the general combustion equation, right? So no matter what hydrocarbon it is, as long as it's complete combustion, it will fall down into this general combustion equation, right? Only you know what is X and Y, right? So this can be used. But now, since at in these equations, we don't know X and Y, so just leave it. X and Y here, doesn't matter, right? Okay, and then right, we want to make this easier, right? Because we have X here and Y here, we want to just put X and Y together. That's the reason why we divide everything by 1 over X, right? So that Y and X will be together, right? So right here. So we divide everything by 1 over X. The reason is we want to put X and Y together because later on we have to work out for Y and X, right? Okay. So from this equation here, you go with the way that you used to do or the way that you were. Okay. The amount of mass for the air is what? Then it's going to be 1 plus Y over 4X. Times with what? The molecular mass. You have 32, 28.16 for oxygen, and nitrogen. And the result show like this. Right? Same thing, you do it for the mass of the fuel. Right? You have this. So you come up with what? This amount, right? In terms of kilograms, right? So the air fuel ratio stoichiometric on the mass basis will be this, right? In terms of y and x, doesn't matter. Okay, so now after we finish this, we are ready, right? If we know y and x, then we just plug in the value y and x into all of this, right? Because we get used to that. Every time that we do the problem on the combustion, I have to go with combustion equation first, right? So we do it based on our belief, and then now we will work out what is the x and y. Okay, so come back to the informations. We have the molecular weight of this fuel equal to 114.15, and this fuel contain carbon and hydrogens, right? So this molecular weight or mass have to be the sum of what? The molecular mass, right, of each one. So we have 12 times with the number of what? Atom here, and this is the molecular mass of the hydrogen times with y here, right? So this is the first equation because it's 1 mole, right? So this is the first equation that shows us the relation between x and y. Okay, x and y here. And then we use the second informations. Right? We have 84.1% of carbon and 15.9% of hydrogen. Right? So that means what? Right? This is by mass. In terms of mole, right? The hydrogen over carbon in terms of mole, right? Because when we talk about in terms of mole, it's gonna be y over x here. So it is what? Mass divided by molecular mass, right? So hydrogen is 15.9% by mass divided by 1.008, which is the molecular mass. Then it's gonna be percent of mole, right? Same as the carbon down here, right? So we have y over x equal to this, right? So we have two equations, two unknown. Then we can solve for x and y, right? X and y here, right? So we know now that the fuel is in fact octane, right? With it C8H18. So we put it back into our general combustion equation, right? Y and X, Y and X, and Y and X, right? Because this is in terms of mole, right? We write it down on the mole basis here, right? So we have to change by mass here into mole, right? Here is already done. Okay, so we put x and y in here. Okay, and then we finish our calculations. So the complete combustion equation show like this, and then we sum the total number of mole, right, for each reactants. We have 1 mole of oxygen and this much amount mole of the air, right, which is 59.66. And on the products, we have 8 mole of carbon dioxide, 9 mole of water, and 47.16 mole of nitrogen. And it's come out 64.16 mole, right? So that means we have about 60.66 mole of the reactants, which will give us 64.16 mole of the product, right? Okay, so in here, right, you find out that the number of mole on the reactants is not equal to the number of mole on the products, right? That is okay, right? The number of mole doesn't need to be equal on both reactants and the products, right? But when we talk about mass, when we talk about the mass, if you want to check that your balancing is correct or not in terms of mass, right? So we time it with the molecular mass, right? On both sides, for each reactant and for each product, right? So we come up with what? 114.5 plus 1727.8. If you sum these two together, it's gonna be this number, 1842.3, which we can get from here, right? So in terms of mass, the mass of the reactants have to be equal to the mass of the product. So this is how you can recheck that your combustion equation is correct or not correct. Right? Why the mass of the reactant have to be equal to the mass of the product? It is because of the conservation of mass. Right? Conservation of mass. We don't have conservation of mole. Right? So the number of mole on the reactants, right, doesn't need to be equal to the number of mole on the products, right? But for mass, it have to be the same. Okay, so this is one way that you can do the checking on your balances, that you balance is correct or not. Okay, so per unit mass fuels, right? If we want to get in terms of per unit mass fuel, so we divide the whole equation here by 114.5, and the result is we have 1 mole of 1 kilogram of oxygen require 15.14 kilogram of the air, right? And the total mass of the product will be 60.14, right? And the stoichiometric air fuel ratio will be 50.14, right, on mass basis. How about the molecular mass of the reactants and the molecular mass of the product? It's just the summations, right? Because we have more than one reactants. We have more than one products, right? So what are the reactants we have? Right? We have the mass of what? The mass of the fuel and the mass of the air, right? Divided by the total number of mole of the products. Then the molecular mass of the whole reactants as one will be 30.36, right? Same thing that we do it for the product. The molecular mass of the product as one product, right, will be the mass of each product summed together divided by what? The total number of mole for the products. Okay. Okay, so that is the combustion analysis, right? That you know how to do the balancing of the combustion equations, and that's always the first thing that you have to do when you go into combustion problem. Okay. The next topic we will talk about the enthalpy of formation. In fact, this material is the old material because most of you already learned in thermodynamics about the enthalpy of formation. Okay, I just review this again for you because some of you might forget. Okay. Enthalpy of formation. What is the meaning of enthalpy of formations, right? So by name, you look at formation. Right? Before that, you know just enthalpy. But now they're talking about the enthalpy of formations, right? So they have the word formation. So that means this enthalpy come out from what? It's come out from the increase in enthalpy when a compound is formed, formations, right? So when we have two elements combined together, right, and we come up with a compound, right, they always have an increase in enthalpy happen because of this, right? Because of this, right? So the enthalpy of formation is the increase in enthalpy because of that, right? And this compound is formed from its composing element in their natural form, right? In their natural form. So is it in the gas, and gas combined together, solid combined together, if their natural form is that, right? Gas, liquid, solid, right? Liquid and solid combined together, right, into compound, right? They always have enthalpy happen, and it is referred to the standard state, 25 degrees Celsius and 0.1 megapascal. Okay, so, and everybody know that enthalpy is the physical it's not a physical parameter, because enthalpy come out from definitions, right? And apart from this, when we talk about the energy in thermodynamics, right, it's not always the absolute energies, right? No matter we talk about enthalpy, we talk about internal energy, it's not that absolute value, right? Not the absolute value, because we don't have the law to find the absolute value of this, right? So it is the reference value or the relative value. In fact, when we set up the reference value, right, for all of this energy, no matter is the enthalpy, no matter is the internal energy, right? So the natural form, right? We talk about the natural form here, right? So the natural form of oxygens, nitrogens, and hydrogens. These are three main important elements in combustion, correct? Right? Oxygen, nitrogen is in the air. Hydrogen is one element in the fuels, right? So because they are important in combustions, right? So we will use these three elements to set up the reference of the enthalpy of formations. Okay. So we set the oxygens, we set the enthalpy of formation for oxygens, nitrogen, and hydrogens, right, to be 0 at the standard condition, 25 degrees Celsius and 0.1 megapascal, because under this standard condition, they are all gaseous. Okay, so in the table, right, the enthalpy of formations for oxygens, nitrogen, and hydrogens, right, at standard conditions is equal to 0. Right? You might wonder, oxygen, right, we have diatomic oxygen, so it can consider to be a compound or not? Yes, I think so. Okay, but anyway, we set the enthalpy to be 0 here. Okay. Okay, how about the enthalpy of formations at any temperature and pressures apart from the standard one? Right. So other enthalpy of formation at standard conditions, right, we will refer to this enthalpy. Right. So at the standard condition, it is always 25 and 0.1, right? Other element or other materials, right, except oxygen, nitrogen, and hydrogen. They all have the enthalpy of formations not equal to 0 at this standard condition. How about the enthalpy of formation that is not the standard, not at the standard conditions? Right? We can find it by using this equation. Right? That is the enthalpy of itself, the enthalpy of formation of itself at the standard condition, plus the change of the enthalpy, right, at any temperatures, right, that is different from the standard conditions. Okay, and if you remember in thermodynamics, right, we have table 8.9 that talk about the enthalpy of formation at standard conditions and the change of the enthalpy at different temperature apart from the standard conditions. Right? We have for nitrogens, diatomics, nitrogen, monoatomics, right? Oxygens for both diatomic and monoatomics. Okay. Also have hydrogens, right, for both diatomic and monoatomics. We also have carbon dioxide, carbon monoxide. We have water, right? We have nitric oxide, nitrogen oxide, or hydroxide. Okay, so all this, right, you can find from table 8.9, right? And in table 8.10, right, in table 8.10, they only show you the enthalpy of formation at standard condition with 25 degrees Celsius, 100 kPa, right? So in table 8.10, you will find the information on the enthalpy of formation for different substances. A lot of this, more than this, I just showed you some examples here. Right? All of this you can get it from the fundamental of thermodynamics, right? The textbook that you use when you learn thermodynamics. Okay, so since we know the enthalpy of formations, right? So now let's get back to our combustion. Right? Because the way we do the combustion, we make a compound happen, right? We make a compound happen. Okay, so to do the analysis, we have to come back to our first law, right? So we start with the first law for the steady state process. Right? We start with this because this is the good start before we get it into our real combustion in our internal combustion engines. Okay, so the first law for steady state process tells us that we have the amount of heat that come out from reacting system, right? We call it QRP, plus the enthalpy of the reactants, right, equal to the amount of work, right, from the reacting system, right, in which we look at our reacting system as a control volume because we talk about the steady state process, right? So we use the control volume approach to do the analysis on our reacting system. Okay, so this is the beginning. Okay, and then we have the enthalpy of the products come out here, right? So this is the first law, right? Then we rearrange these equations, right? So we have the heat that transfer from general reacting system at any temperature T, right, will be the enthalpy of the product at temperature T minus the enthalpy of the reactant at temperature T plus the work, right? Here we start with the temperature of the product same as the temperature of the reactants. That means what? That means we wait until our product cool down to the same temperature as the reactant. right? And get all the amount of enthalpy that release, right, until the temperature of the product same as the temperature of the reactants. Okay, so this is our beginning, right? Then, right, the enthalpy of the product and the enthalpy of the reactant can come out from what? The enthalpy of formations, because it's a compound. Okay, right? We react the compound. So the enthalpy of the product and the enthalpy of the reactant come out from the enthalpy of formation. So right here, right, time with the number of mole for each product and for each reactant, right? The enthalpy of formation, right, we can get it from what? The enthalpy of formation at standard conditions plus the change of the enthalpy, right, due to the temperature that difference from the standard conditions, right? Same thing for the enthalpy of formations for the reactants, right? So notice this is the enthalpy of formation. This is the enthalpy of formation at standard conditions. Okay, difference. Okay. So this is how we can get the amount of the heat. If we wait until our product cool down to the same temperature as the reactant. Okay. So let's look at the examples, how we can make use of the equation that I just showed. Right. Consider the following reactions which occur in a steady state, steady flow process. Right. We have C6H6 plus 7.5 react with oxygen only. Right. And the result of the product is carbon dioxide and water as a vapor. Okay, so the reactant and the product are each at the total pressure of 0.1 megapascal and 25 degrees Celsius. Right. Some students might think, how come the product can be at 25 degrees Celsius? It can. Only you give them time to cool down. Right? So that means after we perform these reactions, we wait until the product cool down to 25. That's very simple. Okay. Determine the heat transfer per kilomole of the fuel resulted from this reaction in the combustion chamber. Okay. So they want us to find the heat that come out. Right. So this is the equation we use. Right. Temperature is 25. We have no work come out because it's just a combustion, right? So the enthalpy of the product and the enthalpy of the reactant at 25 degrees Celsius can come out from the enthalpy of formations. So look at the reactants. We have two reactants. One is C6H6. Another one is oxygen, right? And our standard temperature is what? 25, right? So that means we have no enthalpy of formations come out from oxygen because we set it equal to 0, right? So we have only the enthalpy of formations come out from the fuel, right? In which we can get the enthalpy of formation at standard condition, 25 degrees Celsius from table 8.10 for the reactants. Same thing for the products, right? We find the enthalpy of formation at standard conditions for the carbon dioxide and also the enthalpy of formation at standard conditions for the waters, right? Both found from table 8.10, time with the number of mole, right? That result from balancing of combustion equations, right? Then we can get the amount of heat, right? and this heat is the heat that come out. So you expect to have what? You expect to have minus sign in front of the heat, right? You expect to have minus sign come out in front of the heat because this is the heat that go out from the system. Okay. So we start with the first law, right, for the steady state process. Now let's look at our system, right? Let's look at our system, right? Our system, the combustion chamber is the cylinder and the piston, and it happened in a closed volume, right? When we talk about a closed volume, the approach that we have to use in thermodynamics is what? A controlled mass, not a controlled volume, right? Not a controlled volume, right? And later on, right, at this point, students may wonder, why don't I teach you the controlled mass at the very beginning? Why I need to teach you the steady state or the controlled volume first? Later on, you will know why I have to introduce to you the steady state or the controlled volume first. Okay, so now our system is a controlled mass, non-flow, right? Because we let everything finish before we let it go out. Right? Everything have to finish and then it can flow out. Okay, so let's look at the first law. How we gonna apply the first law to our combustion process. Consider a non-flow or controlled mass combustion process that happen in the piston and cylinder, right? We have the reactant right here, right, at the initial condition, which is at the volume V1 and T1, right? Forget about these two first, right? We have reactant here, and when we finish, we have the product right here with V2 and T2 here, right? So we starting with a mixture of fuel and air reactant at state V1, T1, and ending with the product at state V2, T2. Okay. Now, notice that the temperature change for the reactant, right, from T1 to T2 and for products from T0 to T2. Okay, this talking about these two, right? The reason we have to put these two pictures in our analysis because we want to make it easier when we do the analysis, right? If we don't have these two pictures, look at the reactant here and the product here. You see the difference from what we usually do in our thermodynamic analysis, right? You see, we have different substances here at the initial conditions and at the final conditions. If you remember in thermodynamics, right, what we usually do is our substance never changes. That's the reason why we talk about the pure substance in thermodynamics. Right? When you do the analysis for the refrigeration cycle, right, you do the analysis for the power cycle as a standard cycle. Your working fluid never changes. The only thing change is the conditions, right? So you can talk about the same mass in your equations, right? You talk about the heat is equal to mass time the enthalpy, the change of the enthalpy, or the mass time the change of the internal energies, right? You have only one mass all the time. Okay, but in here, you have the same amount of mass, but it different mass. Correct? Right? You have the same amount of mass. We just mentioned conservation of mass. You have the same amount of mass, but it different mass because it different substances. We have reactant here, we have product here. That's the reasons why we have to put these two pictures into our analysis. The first one is the reactants at V0, T0. The second one is the product at V0, T0. Okay, so that's why when you look at this, you notice that the temperature change for the reactants from T1 to T0. And for the products, it changed from T0 to T2, right? So now we have the same pictures, right? We have the same amount of mass and also the same mass. The difference is the conditions, right? We have the same picture that we used to see in thermodynamics, okay? So in here, we start with this, right? So since it is a controlled mass, right? So the energy that involved with the controlled mass is the internal energy, right? In fact, I should not call energy, it's a property, right? The property that involved with the controlled mass is the internal energies, right? So if we want to find the internal energy change between state 1 and 2, right? By looking at this picture and these pictures. This is what we have. U2 minus U1 is UP2 minus UR1. Okay, right? So this is the original picture, right? Right. So we write down what we used to, right? Except that we notice that this is the mass of the product. This is the mass of the reactants. Okay. So we will change this into our new picture. So like this. Right. So what we have is we have the internal energy of the products at 2 minus the internal energy of the product at T0 plus the internal energy of the product at T0 minus the internal energy of the reactant at T0 plus the internal energy of the reactant at T0 minus the internal energy of the reactant at T1. Right? And if you sum all this together, you get the same here. Right? This is what engineers always do. Look at the same thing on different picture in order to ease our analysis. Okay, right. This is the principles. Same thing on different pictures, just to simplify the analysis. Okay, so when we look at this, you see, you notice this. The mass is different, but the condition is the same. The mass is different, but the condition is the same. And if you go back to here, the same thing, the mass is different, the condition is the same, right? Okay, so now you see some related, okay, something that related with each other. Another two terms, the mass is the same, the condition is different. Okay, so UP2 minus UP0 and UR0 minus UR1 represent the change of internal energy due to the change of the conditions. Right. Okay. T0 and T2 and T0, T1 and T2. Right. Not involving the chemical reaction, correct? Right. Not involve chemical reaction. So we look at the combustion as if there are some portion that not involved with the chemical reactions, right? And that portion is this too. And some involved with the chemical reactions because it changed from reactants to products. Okay, right. So the middle term here represent the chemical reaction. So we have, if we combine all these three pictures together, right, we have the change of the condition. We see the change of the condition. We see the reactions. Right. Before that, we talk reactions, right? And reaction involved with the change of the substance and also the change of the conditions, right? So we just decouple this, right? Decouple this. Isolate. Reaction is reactions. Change of condition is change of conditions, right? The result is the same. The result is the same. Just make our work easier. Okay. So UP0 and UR0 represent the chemical reaction from reactants to product during B to C. This is this. Okay. In constant volume, constant temperature, right? Because 0 and 0 here, and no work. Okay. So we will define this middle term, delta U0, which is UP0 minus UR0. Call is the internal energy of combustion at T0. Right. So in overall, now we have UP2 minus UR1 equal to UP2 minus UP0 plus delta U0 plus UR0 minus UR1. Right. Where the less here, these two terms here, we can find it from what? From our knowledge in thermodynamics. Right. UP0 minus UP2 minus UP0 equal to what? Summation of the mass of the product. Right. How many products you have times with the specific volume at constant volume times with the change of the temperatures. Or if you want to go into more accurate results, then you will use the property called internal energies of each products at T2 minus the internal energy of that products, right, at T0. Right. Same thing for the UR0 minus UR1, the same thing. Okay. Now, okay, we have this internal energy of combustion, delta U, right? Delta U0. Now we want to relate this to enthalpy because we only have the table of enthalpy of formation. We never have the table of internal energy of formations. No, okay, we don't have that. So similarly, right, if our combustion process happen to be a steady flow, a controlled volume, right, it have in what machine? Not in our internal combustion engine, right? The steady flow combustion process happen in the gas turbine engines. Okay, right. So for that, since it is a steady flow, right? So the approach that we have to use is a controlled volume, right? For steady flow is steady, show right here. So give you a sense of what? You have mass flow in and out, flow in and out, flow in and out, right? The word steady give you a sense of this. You see the mass flow in, flow all the time, right? No matter it in and out or in, oh no, in and out, correct. In and out, it's a steady flow, right? Steady flow, okay. And that means we have to use the control volume, okay. So, and by that, we can use the same picture, right? We have enthalpy of product at T2 minus enthalpy of the reactant at T1, right? For steady flow control volume, the property that we have to use is the enthalpy, okay? That means this difference will be equal to what? Enthalpy of the product at T2 minus enthalpy of the product at T0 plus delta H0, which is what? The enthalpy of the product at T0 minus the enthalpy of the reactant at T0, right? The material change, but the condition is the same, right? Plus the enthalpy of the reactant at T0 minus the enthalpy of the reactant at T1, right? And this delta H0, we call it the enthalpy of combustions at T0, right? And it is always negative, right? Because we talk about heat that come out, remember? So this term refer to what? Refer to here. Refer to this term in which we can find from the table of the enthalpy of formations, right? So these two terms, we can get it from the table of enthalpy of formations, right? So now, okay, and the other two terms, right? The other two terms, we can get it from the mass times with the specific heat at constant pressures times with the temperatures, right? Or if we want to get the accurate result, we can use the enthalpy, right? The table of enthalpy, not the table of enthalpy of formation, right? Because nothing formed, the same material happened, right? No new material formed from the process, okay? So this is just enthalpy, right? Same as the reactant here, right? Reactant and reactant, no new material come out from the process, right? So this is just the enthalpy due to the change of the condition, not because of there is a new compound come up. No. Okay. So now we know we have the internal energy of combustions. We have the enthalpy of combustions. How we gonna relate these two together, right? Because we only have the table for the enthalpy of formations. We do not have the table for internal energy of formations. Never have, right? So how we can relate these two together so that we can get the value for the internal energy of combustion here, right? So go back to the definition of the enthalpy, right? I already mentioned this is not physical property, right? It come out because we define it. It's different from other property. That is a real physical property, right? So we have enthalpy equal to U plus pressure times volume, right? This is the definition of enthalpy, right? The reason we have to define enthalpy because we have a flow process. That's the reason why, right? That's the reason why. When we have a flow process, this is the energy required for that flow to happen, right? pressure and volume time together become work. In thermodynamics, we call this term a flow work. If you remember, it is a flow work, right? Because we have flow, so we need some work for that flow to happen. Apart from the existing of that material, which show in this U, the internal energies. Okay, so the enthalpy come out because of this, right? So we have enthalpy equal to U plus PV, and this PV, right? If our working fluid is a gas, right, with the moderate density, which is always, right? Because when we perform combustions, right, we don't put it that hard so that the density is dense, right? So under moderate density, this PV can be represented by a perfect gas equation, which is what? N mole times R bar, the universal gas constant, times with the temperatures. Okay, so H enthalpy of the product at T0 will be equal to the internal energy of the product at T0 plus the number of mole for the product times the universal gas constant times with T0. Right. Same for the enthalpy of the reactants here. So in here, now we can come up with the equation that relate the enthalpy of combustions and the internal energy of combustions, right? So now we can use the table of enthalpy of formations in order to find the internal energy of combustions right here, okay? So from these equations, the same one here, you can see that if there is no change in the number of mole during the reactions, right? That means the number of mole for the reactants and the number of mole for the product, they are the same. That one conditions. Or if the reference temperature, which is T0, right? If we do it at absolute zero temperatures, right? That means if we perform these reactions at absolute zero temperatures, right? Under these two conditions, either one, right? You will find that the internal energy of combustions will be equal to the enthalpy of combustions. Okay, right. So let's look at the example. Calculate the internal energy of combustion, delta U0 in kilojoule per kilogram for the combustion of benzene with its C6H6 vapor, which react in a constant bomb at 25 degrees Celsius standard condition with oxygen, react with oxygen, and the product, right, which is water H2O, is in the vapor phase, right? The constant bomb is a device that we do the combustions under constant volume, or it's a closed volume. Okay, so it's a closed vessels to perform the combustions. Okay, so again, right, even though we come up with the new material here, the internal energy of combustion, we still have to rely back to our basic graph, right? The combustion equation. We have C6H6 react with oxygen. The product come out as CO2 and water, right? So we do balancing the equation. We find out the number of mole of the reactant will be 8.5. The number of mole for the product is 9, right? So to find the internal energy of combustions, we make use of this equation. Our T0 become the standard temperature condition, 25 degrees Celsius, right? So now, in order to come up with the internal energy of combustions, we already know the enthalpy of combustion here from our previous example, right? we talk in terms of the heat that transfer out. Same thing, right? If you remember, it depends on which one that you would like to talk, right? If you talk on this side, you said heat transfer. If you talk on this side, you said the change of the enthalpy. Okay, so in here, right, we talk about the enthalpy of combustion or the change of the enthalpy, right, when the material change from reactant to product under the same conditions. Okay, right, so this is the meaning of the internal of the enthalpy of combustions, as well as the internal energy of combustion. We're talking about the change of the enthalpy, right? When the condition is the same, but the material change from one substance to another substance. Okay, so in terms of enthalpy, it is become the enthalpy of formation because it forms a new substance. Okay, so from previous example, we already have the heat transfer, which is equal to enthalpy of combustion, right? Or the change of the enthalpy under the same conditions, only the material that changes. Okay, so this is the amount we have, right? So the internal energy of combustions, right, can be found from this, which is this on the mole basis, right? Because it's kilojoule per kilomole. So on the mass basis, we just change mole into mass using the molecular mass. So it is 40,000 something kilojoule per kilogram of the fuels, right? So in here, I think everybody understand the meaning of internal energy of combustions and enthalpy of combustions. Okay. Another example, calculate the enthalpy of the product and the reactants. Okay, and the enthalpy and internal energy of combustions of the stoichiometric mixtures of methane and oxygen at 298.15 Kelvin, which is the standard conditions. Right. Okay. So our stoichiometric reaction is this. This is our methane. Right. Methane and oxygen react together, right? Balancing the equation. This is what we get. Okay. So go to the solutions. Right. The enthalpy of the reactants at 25 degrees Celsius, right, is what? Is this methane, right? Oxygen is 0, right? So we get it from 8.10, the enthalpy of formation at standard conditions, times with the number of mole, right, for the methane, right? For the products, right, if we consider that this water, the water shown right here, is a vapor, right? So the enthalpy of the product at standard conditions, right, consists of what? The enthalpy of formation at standard condition for the CO2 plus the enthalpy of formations at standard condition for the water as a vapor, right? As a vapor, right? Both of these we can get it from table 8.10. Okay. If it is a liquid, then this water, the enthalpy of formation for the water, have to look for the water when it is in terms of liquid. It's also shown in table 8.10, right? So you see two enthalpy of formation, right, at the standard conditions for water. You see two of them here in table 8.10. It depends that you look at the water as a liquid or as a gas. Okay, so we have the enthalpy of the product finished. Now calculate the enthalpy of combustions. Right. So if the water is vapor, the enthalpy of combustion at standard condition, right, the enthalpy of combustion at the standard condition will be the enthalpy of the products minus the enthalpy of the reactant at the same standard condition, right? This is the meaning of enthalpy of combustions. The material change, the condition is the same. Okay, so this is what we have. Right? If water is vapor, if water is liquid, we get a different one. Right? And you can notice that if we let until the water condense as a liquid in our bomb, the amount of the enthalpy of combustion is higher than the amount that we get when we let our water is in the vapor phase. Okay. How about calculating the internal energy of combustions? Right. So back to our combustion equations and back to our equation, right, that relate the enthalpy of combustion to the internal energy of combustions. Right. We have the number of moles shown right here. Right. So if our water is vapor, right, the number of mole of the reactants will be what? 1, which is fuel, 2, which is for oxygens. How about the number of products? We have 1 carbon dioxide plus 2 water, right? So it's 3 equal to 3. So the number of the reactants equal to the number of the product. So that means when our water is a vapor, we have the internal energy of combustion equal to the enthalpy of combustion. But when our water is a liquid, you see the number of the product here now reduced to just 1 because we don't have water as a gas or as a vapor here, right? So the internal energy of the combustion now will be different for the enthalpy of combustion, right? To what amount? To this amount. Okay. Okay. So okay, we will take 10-minute break here. Any questions? Hello? 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 เงียบเลย ฮัลโหลได้ยินหรือเปล่าเงียบเลยเว้ย
ได้ยินครับอาจารย์
โอ้โห ตกใจเนี่ยจะมาดู iPad ว่ามันสายมันตัดหรือเปล่านะเนี่ย
ได้ยินครับอาจารย์ได้ยิน
โหนึกว่าหายไปหมดแล้วเนี่ยต้องมานั่งสอนซ้ำหรือเปล่าเนี่ย เพราะว่ามันไม่โชว์นะในหน้าจอมันไม่โชว์หรอกว่าอินเทอร์เน็ตหายหรือไม่หายนะอย่างนั้นเดี๋ยวเราพัก10 นาทีนะครับนะก็เดี๋ยวกลับมาตอน 11:10 นะครับโอเคครับ
ครับ
Okay, we get back to our lectures. I think everybody ready. I cannot move my slide again. Stop share. Okay. Okay, let's get back to our business after a break. Okay, we talk about the reference temperatures, right? We talk about the standard conditions, right? With 25 degrees Celsius, right? We talk about the internal energy of combustions. We talk about the enthalpy of combustions, right? And we use T0 as reference temperatures. Okay. Now, if we want to change the reference temperatures, right? How we can find the internal energy and enthalpy of combustions, right? At temperature apart from reference temperatures or the standard condition temperatures, right? The internal energy and enthalpy of combustions depend on the temperature at which the reaction occurs due to the change in enthalpy and the internal energy of the reactant and product with the temperatures. Okay, so it changes, right, depend on the temperatures. So from our equations that involve with the internal enthalpy of combustion right here, right? And this is the change of the enthalpies, right? From products to the reactants at different conditions, right? We call this the enthalpy of combustion at any temperatures. Let's call this term the enthalpy of combustion at any temperature. And we put it the minus sign here, right? So from different condition here, we just change it to be the same conditions, right? From this equation that involve with the different condition, 2 and 1 here show you the different condition when it is in the products, when it is in the reactants. Now we want to talk about the enthalpy of combustions at any temperature, right? So that means it have to be the same temperature, right? So the final condition and the initial condition, they are the same temperature, right? So this term become the enthalpy of combustion at any temperatures. And we put the minus sign here. We put the minus sign here. So that means what? This term, 0 or 2 here have to be T, right? And we have the minus sign here. And this delta H0, right? Also still the same, right? Because it's T0. Right? We want to show you that apart from reference temperature, how much it's gonna be for the enthalpy of combustions, right? So the minus sign here will be affected by the plus sign here will be affected by the minus sign that we put here. So it get the minus here, right? Okay. And then the last term here, right? The initial condition T1 become at any temperature T here, right? And we move from back into front. So the plus sign is still here, not get affected, right? Because we move this term in front here. So we have HRT minus HR0. See, so we make use of the equations, right? That find you the change of the enthalpy, really change of the enthalpy, right? Because it product to reactant and different conditions, right? We make use of this. Only modification that we make it, we use the same temperature here, right? So this term can be called the enthalpy of combustion after we modify to the same temperatures. Okay, so this delta HT, right, from this equation, you can see that we can obtain this delta HT from delta HO at T0 from above relation. Right. So this will tell us how we can get the enthalpy of combustion at any temperature. Right. If we do have the enthalpy of combustion at the reference temperatures. Okay. So I make a plot here for you to see, right, from this equation. Okay. This is the enthalpy, this is the temperatures, right, and make plotting two lines. One line is for the product, another one is for the reactants, right? So if you follow along this line, right, what you see is what? You only see the change of the product at different temperature, right? If you go along this line, you only see this. Same thing, right? If you go along reactant, you only see the change of the enthalpy of the reactants. Right. This is what I mean that you usually deal with these two in thermodynamics. Right. Refer to refrigeration cycle or the power cycles, right, as standard cycles. But if you go from reactants to product or product to reactants, this is what you see. Right. The change of the enthalpy, right, from reactants to product under the same condition. Right. Or here, right, under temperature T, you jump from product to reactants or reactant to product. This is what you see. Right. The change of enthalpy from reactants to products at the same conditions. Yeah. So this picture will give you a clear understanding what you have learned so far. Okay. Examples. Okay. Enthalpy of combustions, right, delta H0, right, for CO reactions at 60 degrees Celsius. Now their reference temperature is 60 degrees Celsius because they use this delta H0. Right. It's given as minus 285, 200 kilojoule per kilomole. Calculate the enthalpy of combustions, delta HT, for the same reactions, CO reaction. But now this reaction happened at 2500 degrees Celsius. Right. They give you the enthalpy of all gases concerned in reaction in terms of kilojoule per kilomole, shown in these tables. Right. We have reactants at carbon monoxide and also oxygens. Right. At reference temperature equal to 60 degrees Celsius, and at temperature apart from different temperature with it at 2500 degrees Celsius. Right. The value shown here is R or enthalpy, right, for these two temperatures for both reactants and the products here. Okay, so for CO reactions, right, again, we have to write down the reaction equation. Right. CO plus half mole of oxygen becomes CO2. This is the reaction that happened. Okay, so from our equation to find the enthalpy of combustion at any temperature, right, we can get from all these three expressions summed together. Right. So at temperature equal to 60, which is 0 here, right? The enthalpy of reactant at 60 degrees Celsius will be what? 1 mole of carbon plus half mole of oxygen. 1 mole of carbon plus half mole of oxygen. The enthalpy, get it from this table. Right. So this is the reactant, the enthalpy of reactant at 60 degrees Celsius. At 2500 degrees Celsius, we do the same thing. Right. 1 mole of carbon, half mole of oxygen, times with the enthalpy at 2500 degrees Celsius. right? So now we're done with this last term. Right? Work out term by term. Right? The enthalpy change of reactants, right? No reaction from 60 to 2500 will be this last term here, right? Yes, we keep it this number here, and then we work the same for the products, right? The product at 60, we have only one product with this CO2, right? The enthalpy show right here, and then we have the product at 2500 degrees Celsius. Same. So the change of the product as if is no reactions because the product is the same. Only the condition change will be this. Okay. And with the given enthalpy of combustions for CO reaction at 60 degrees Celsius, which is given like this. So the enthalpy of combustion for CO reaction at 25 degrees Celsius will be this. Right. So the same reactions, but with different temperature, you get different enthalpy of combustion that happen. Okay, this go back to our basic knowledge. Fuel, air react together at elevated temperature. Right. So what is that elevated temperature? What is the effects on the elevated temperature to the results of combustions, right? At different elevated temperature, you get different amount of heat. In here, we call it enthalpy of combustion or internal energy of combustion, right? For the same fluid, for the same amount of mass, for the same thing, you only change the temperatures. You get different results, right? Very simple. You pay the same money. You sit on Toyota and you sit on the Benz. Get different feelings, right? Okay. You the same. You yourself is the same. Sit on Toyota, sit on Benz, different the same. Okay. So with this, you can easily understand the material here. Okay. Okay, so let's get to another one, adiabatic flame temperatures. Adiabatic flame temperatures. Okay, what is the adiabatic flame temperature? This, in fact, is the same material that you learned in thermodynamics, right? Just go back and review for you. The adiabatic flame temperature is the temperature that attained in combustions where we have no heat transfer, no work, or no change in kinetic and potential energy. So that means what? That means what? This is the maximum temperature that can be achieved. This is the maximum temperature that we can achieve from our combustion because we don't let anything to go out from our combustions. No change in kinetic energy, potential energy, no work, no heat transfer, right? This adiabatic temperature can be achieved with the stoichiometric mixture when complete combustion. So apart from letting no heat, no work, no change, right? Our combustion have to be complete combustions under stoichiometric mixtures. Okay, so examples to find the adiabatic flame temperatures. Okay, liquid heptane C7H16 had an enthalpy of combustion at 25 degrees Celsius, which is standard temperature, equal to 44,560 kilojoules per kilogram, when the water in the product is in the vapor phase. So this is the amount when the water is still in the vapor phase. This fuel is to burn adiabatically, no heat transfer, in a steady stream of the air, right? in a stoichiometric proportions. Now, if the initial temperature of the fuel and air is 15 degrees Celsius, right? So the reactant is at 15 degrees Celsius. Estimate the temperature of the products. What is the temperature of the product here? Right? The specific heat of the liquid heptane, which is the fuel, at constant pressure is 2.30 kilojoule per kilogram. They give us the specific heat at constant pressure because it burns under a steady stream of the air. So it burns as the air is keep flowing in and out, flowing in, flowing in, flowing in and out. Okay, so the specific heat have to be the specific heat at constant pressures. Okay, again, come back to our belief. Right? We have to start with the combustion equations always. Okay, so we have C7H16. We do it with the air, and we come up with the complete combustions. This is the results from balancing the combustion equations. This is the first thing that we have to do. Okay, then the first law for the steady flow: no heat, no work. Result is what? The enthalpy of the products equal to the enthalpy of the reactants, right? This is the result that we have under this burning condition or combustion condition, right? So in other words, the enthalpy of the product at the temperature we are looking for, because this is the temperature of the product, minus the enthalpy of the reactant at the initial temperature 15 have to be 0, right? So from these equations, we expand it because we want to find the temperature here, right? So we expand this to be the same picture as we mentioned, right? We have the enthalpy change of the products from the final temperature to the standard temperature 25, plus the enthalpy of combustions at standard temperature 25, plus the change of the enthalpy of the reactants from standard temperature 25 to initial temperature 15. Okay. Okay, so calculate one by one, right? Change of the enthalpy of the reactant first. We know the temperatures 25, we know the temperature 15, right? Is equal to what? The change of the enthalpy here times with the mass. The mass can get out from the molecular mass times with the mole for the fuel, right? The fuel, we have no table for the enthalpy, so we use Cp delta T. Right. For oxygens, which is also the reactants, show right here. And for the nitrogen, another reactant show right here. Right. The enthalpy change for both oxygen and nitrogen, we can get it from table 8.8. Right. You can get it from table 8.8 because we in table 8.8 we have the enthalpy value for oxygen and also for nitrogen at different temperatures. Right. So table 8.8 in thermodynamics, you can get it. Right. So this is one thing that you should know. Right. What information that is available for you to pick up. Right. Not only the content in the textbook, but all the table. Right. This is the information for you. Right. Depend that you know that there is information like this in the books or not. Okay, so you pick up the information from table 8.8. Then you can do the calculation and you get the change of the enthalpy of the reactants, which is this. You do the same thing for the change of the enthalpy of the product. No reaction, you get the same product out for different conditions. Right. Now, for this one, you don't know these temperatures. because this is the temperature you are looking for, the temperature of the product at final condition. But anyway, never mind, just work it out, right? Just work it out. Because you believe in this, you have to also believe in here. So you work it out with 25 degrees Celsius that you know, right? Okay, this is table 8.8, right? 8.8, that you see you have enthalpy for different temperatures. Okay, you work it out, you know that you don't know the temperatures of the product, right? So that means what? You have to assume, right? Because you know that this amount and this amount have to be what? The same. It have to be the same, right? So this is the condition that will help you to find the temperature. Only that you cannot work it out directly, right? Because you have to get the information from the table. So you go for assuming, right? Then some student might say, oh, it's a trial and error problem, not fair, right? Because I don't know how much that I have to do the trial and error, how many times, right? No, that is not for this one. Not all the trial and error problem give you a headache, right? Because you know that these two amounts have to be the same, right? So if you assume the temperatures, right, you may come up with the change of the enthalpy of the products higher than the change of the enthalpy of the reactants, right? If you assume the temperature, you may come up with this term higher than this. This term you already know, right? So that means when you go for the result of this, you have something that greater than 0. And if you do another assuming, you may come up with the enthalpy of the product here less than this. So your result will be less than 0. And that is enough, because then you can make a plot, right? You can make a plot. And then let's see that the line that you plot, right, intersects with the number of 0 for the enthalpy at what temperatures, and that is your solution, right? Okay, some students might not be able to know that. I show you here, right? This is enthalpy, the result of enthalpy between product minus the reactant, and this is the temperature. So your first assuming temperature give you this much enthalpy of the product minus the known enthalpy of the reactant. You might come up with this positive side, right? Another assumption give you negative side. Then you make this. This is your result temperature. Okay. So not always the trial and error problem is difficult. Not always, right? Because you have condition to know that where is the results, where is the correct results. Okay. So here we first assume that the temperature is 1800 Kelvin for the first estimations, right? So from the tables, right, you can get the enthalpy of CO2, you can get the enthalpy of water, right? For the first one is at 1800 Kelvin, right? The second one is at 25 degrees Celsius, right? You opt it, you can get it from table 8.8, right? So you have the product that is CO2, water, nitrogen. You sum it up. This is the number you get from your first estimations. Come back to these equations, right? You know the enthalpy of combustion at 25 degrees Celsius, right? Because it's already given right here, time with the mass, right, of the fuels. Okay, you sum everything in here, in this equation. You know this one, you know this one, and you know this. Okay, this one you know from here, right? This one from the previous slide, which is cannot go again. Oh, cannot move the slides. Okay, stop share. And do share. Okay. Okay. So this term you get it from here, and this term you get it from here, and this term you get it from here. Right? So overall result is minus, not equal to 0. Right? So you do the second assuming, go for higher temperature, 2000. You do the same thing, you get less minus sign. So that means what? You are now in a good directions, a correct directions, right? Because you're negative while you getting reduced. That means you are traveling closer and closer to 0, right? So you do another one, right? Go for much higher temperature, 2500 Kelvin. This is what you get, a plus sign. That's it. Only 3 assuming temperatures, right? You get this amount, not that amount. Okay, this is the result. Okay, you get this amount. A plus sign show right here. Right? So with all these 3, you make a pot, or you do a linear interpolations. You come up with these temperatures. Either way, you make a pot, or you do the linear interpolation because it's linear. Right? So you get the result temperature, which is the adiabatic temperatures. Okay. Okay. So everything that we learn about internal energy of combustion, enthalpy of combustion, right, we learn in this class. But when you go outside, people don't say internal energy of combustion. People don't say enthalpy of combustion. What they do say is, they will do say calorific value of the fuels, or the heating value of the fuels, right? So in the fuel specifications, right, the quantity delta H0 and delta U0, which is the internal energy and enthalpy of combustion, are approximately by quantity called the calorific value or the heating value, right? It said approximately because we calculate it theoretically, right? But the real calorific value or heating value normally obtained from performing an actual combustion of the fuel in a constant volume type apparatus, which we call is a bomb calorimeter, or in a constant pressure steady flow type apparatus, in which we call is a boil calorimeter, right? So they are equivalent, but they are not equal, right? For internal energy of combustions and enthalpy of combustions, right? When we talk about the calorific value or the heating value, they are equivalent, but in terms of quantity, they are not the same. Because outside, if they want to find the heating value, they just take the fuel and perform the combustions, right, inside the apparatus, right, either bomb calorimeter or boil calorimeter. Okay, so this is the picture show you the bomb calorimeters, in which we have a closed vessel in here, right? because it's capped with this one, so it becomes a closed system, right? A constant volume, right? Or closed volume. And we have another vessel outside in which we fill with water, right? Our fuel sample is put in the crucible, a small vessel here, right? And we ignite this fuel using a field here, right? That we connect via the electrode here. Inside here, we fill with oxygen, right? So we have the oxygen inlet valve here. So we perform a combustion. After combustion happen, right, the heat transfer out to the water. We measure the temperature of the water using this thermometer before and after, right? So we can calculate amount of the heat that transfer out, right? Which is the calorific value or the heating value of the heat practically, or internal energy of combustion theoretically, right? By using the mass of the water times the specific heat of the water times the temperature difference, right? So because mass receive all the heat from here, everything are insulated, no heat transfer to outside. Okay. How about the boil calorimeter? The boil calorimeter, right? This is the apparatus. We have a gas meter, so the gas keep flowing in. Right? We adjust the pressure of the gas to the pressure regulator, right? So the gas flow in, we ignite it, right? The exhaust come out, right? So the exhaust fall out, and we let the exhaust go to the stack here, right? So the combustion keep happening. The combustion keep happening because we let the gas flow in all the time and the exhaust flow out all the time. So that is a steady state conditions, right? And then we have the water surrounding these vessels. Right? We let the water flow in and out. Right? For here, the water is not flow in and out. Right? It keep in here. We have the same amount of water. But in here, we let the water flow in and then out here, right? After it receives the heat. So we measure the temperature of the water before getting into our calorimeter, and then we measure the temperature of the water when it flow out. Right? Again, we time it with the mass flow rate of the water, it with the specific heat of the water, right? So we get the heating value or the calorific value, right? Which is equivalent to the enthalpy of combustion, because this is under steady state process. Okay. So to do that, right, as we already mentioned, right, we can wait until the water from the combustion condense and become liquid, right? So we have two values for the calorific value, right? The first one is called the higher or the gross calorific value, right? At constant volume, right? So with this, theoretically, the gross calorific value at constant volume is equal to the internal energy of combustion, right? And internal energy of combustion at reference temperature, right? If we do it at 25 degrees Celsius, right, the standard one, right? And that means in order to get the gross here, right, the water products have to be in the liquid phase. That means we wait until the temperature go down below the saturated temperature, right? At 25 degrees Celsius, you know what is the pressure inside that can make this reference temperature become the temperature that below the saturated temperatures, right? So that you can be sure that the water vapor in the exhaust will be condensed to the liquid, right? And then If you let this water product still in the vapor phase, in the vapor phase here, right? Then the calorific value that you get is called the roller or the net calorific value here. Okay. Same thing for the constant pressures. Right? You have a higher calorific value at constant pressure, and you also have the lower or net calorific value at constant pressure. Same thing, you let the water condense or you let the water still in the vapor phase here. Okay. So that means what? The difference between the gross and the net, right? It depends on the heat that change the water from vapor to liquid, right? In which we can use this to create the equation that relate the gross calorific value to the net calorific value for both the constant volume and constant pressure, right? In which for constant volume, right, this is the amount of heat that released when water become liquid, right? We use UFG. I think everybody still remember UFG, right? And for constant pressure, we use HFG, right? When water is in liquid, right? I give you here the value for UFG at 25 degrees Celsius and HFG at 25 degrees Celsius, right? And MC is the mass of the condensed water, okay, per unit quantity of the fuels. Okay, so example, the gross calorific value at constant volume of kerosene in Thai, we call it น้ำมันก๊าซ okay, kerosene C7H14, whose ultimate analysis give us 86% of carbon and 14% of hydrogen, right? The gross calorific value of this fuel was found by experiment, so that means they making a real combustion, and they get the value equal to 46,000 something kilojoule per kilogram, right? So this is done under the constant volume. They want to use this information of the calorific value to find the other three calorific value, that is the net at constant volume, the gross and net at constant pressure. Right? So again, see, even this problem, we still have to start with what? Combustion equations, right? C7H14 react with oxygen, right? Because they're done by experiments, and from our experiment, we only use oxygen. So oxygen is the only reactants here, right? So they do it, complete the balance and complete or balancing the combustion equation. This is the result they have, right? CO2 and water, right? So on the mole, on the mass basis, this is on the mole, on the mass basis, right? 1 mole of fuel times with molecular mass of the fuel. 10.5 mole of oxygen times with the molecular mass of the oxygen. The same thing done for the products here. So that means what? If we divide everything here by 98, right, the information give us that 1 kilogram of the fuel requires 3.43 kilogram of oxygen. And this will give us 3.14 kilogram of carbon dioxide and 1.29 kilogram of the water. This is the amount that we are looking for in order to be able to find the other three calorific value here, right? So back to our equations, right? The net equal to the gross minus the latent heat, correct? This is generally we call it the latent heat, right? So the latent heat is what? 1.29 times with UFG here for the constant volume, right? For latent heat, use internal energy under constant volume. Okay, and then this is what the net calorific value, right? And then we know that the gross, right, the gross calorific value at constant volume is equal to delta U0, and the net and the gross calorific value at constant pressure is equal to delta H. So that means what? Right. The gross calorific value at constant pressure equal to the gross calorific value at constant volume plus the enthalpy of combustion minus the internal energy of combustion. Okay, so now student might wonder how I can come up with this relationship. In fact, this is a tricky equation because if you sum this side together, what do you get? You will get the gross calorific value at constant pressure equal to the gross calorific value at constant pressure, correct? Right? The same is the same. That's what this equation said. The same is the same. But we make use on the same is the same by changing it from the same is the same to the same that is not the same but still the same. Right? The same that is not the same but still the same by introducing these two here. Because these two will give us this. This is the meaning that I said not the same. The same that is not the same, but the whole thing still the same. Okay, so this is what we have, and we can find, right, the mole of the product and the mole of the reactant from what? From these equations or this, right? By changing this mole into mass. Change to get the mole, we have the mass divided by the molecular, right? Because we know the mass from here, the products and the reactants. So we divide by the molecular mass in order to get the mole, right? Or you can use this one, right, which is the same because this show you in mole already. Okay, either one can use. And then you time with the universal gas constant, time with the temperatures, right? Then you get the gross calorific value of at the constant pressures. And then the net calorific value at constant pressure can be found from the HFG here. Okay. So this is how we can come up with only one information that is given and find the last three informations. Okay. Okay, I think this is almost near the last. Huh? Combustion efficiency of an internal combustion engines. Okay, the combustion efficiency, right? In general, right, in the exhaust gas of the internal combustion engine contain the incomplete combustion product. This is what happened, right? Generally, when you do the exhaust gas analysis, right? And that means incomplete combustion is that product is that you have CO, you have hydrogens come out. You also have the unburned hydrocarbon or the hydrocarbon that left over, and you have soot that come out. Right? Soot is a particle, a big size particle. We call it a soot. Okay, as well as a complete combustion product, which is CO2 and water. Right. So the exhaust gas come out with both incomplete combustion product and complete combustion product. So under lean operating condition, that means if you using lean mixture, the amount of incomplete combustion product are small, right? So if you go for lean mixture, these amount are small, but for the rich mixture, this amount become more substantial. That means are no longer small. So why for rich mixture the amount of incomplete combustion are getting more substantial? Because there is not enough oxygen to perform the complete combustion, right? So that means you don't have enough oxygen to react with the fuel. So not all of the fuel chemical energy that can be released inside the engine during combustion process. This is the fact, right? This is the fact. So that means we have to have a combustion efficiency to see how good that we do the combustions, right? And the combustion efficiency come out from the enthalpy of combustion, right? At any temperature. The enthalpy of combustion at any temperature divided by what? The amount of heat that we provide to the combustions. Right? The amount of heat that we provide to the combustion, which can be calculated from the heating value. QCV represent the calorific value or the heating value, and what? The mass of the fuels. The mass of the fuels, right? So this is how the combustion efficiency come up. Okay, and if we make a plot, between the combustion efficiency that we receive and the exhaust equivalent fuel air ratio, right? In which we know that at the equivalent ratio equal to 1, we have the stoichiometric. So anything that less than 1 is a lean mixture. Anything that greater than 1 is a rich mixture, right? And we perform under difference value of the equivalent fuel air ratio and determine the combustion efficiency. This is what we have. Right? So in here, you can see that if you go for the lean mixtures, right, you have what? Higher combustion efficiency, right? In which for the spark ignition engine, lean equivalent fuel air ratio will provide higher combustion efficiency than rich equivalent fuel air ratio, right? We have to say this because for the SI engine, we can go for either lean stoichiometrics or rich, if you remember, right? But for the CI engine, usually we go for lean. If you remember when we talk about air fuel ratio. So for CI engine, since it always go for lean, right? The combustion efficiency is normally high. Right? High. Okay, so that's it for today. Any questions? Any questions?
อาจารย์ครับ
ครับ
ถามเรื่องการบ้านได้ไหมครับ
อะไรนะ
ถามเรื่องการบ้านได้ไหมครับ
อ้าวถามการบ้านเหรอการบ้านชุดไหนอะชุดไหนชุดที่ผ่านมาหรือชุดนี้ยังไม่ทำสิใช่ไหมชุดที่ผ่านมาฮะทำไมเหรอไม่รู้ตอบได้เปล่านะ นะมีติดอะไรเหรอ
ข้อ 2C ที่อาจารย์ได้หาความเร็วกับ crank angle ครับอันนั้นต้องทำยังไงครับ
ความเร็วเรามีสมการหาอยู่แล้วนี่มีหรือเปล่าเดี๋ยวขอดูการบ้านก่อนจำไม่ได้all material homework การบ้าน2ใช่ไหมคือทำไมล่ะการบ้านอันที่2อันนี้แชร์ยังวะยังใช่ไหมเดี๋ยวแชร์ก่อนแชร์ยังแชร์แล้วนี่homework 2อันนี้ใช่ป่ะ
ใช่ครับข้อ 2C ครับอาจารย์
ข้อ 2C calculate the crank angle location for peak velocity right for both configuration ใช่ไหม engine มีบล็อกเท่านี้ center piston offset 1.5 connecting rod length เราก็เขียนสเก็ตก่อนใช่ไหมเสร็จแล้ว calculate piston position แล้วหาตัว crank angle position for peak velocity คุณมีระยะทางการเคลื่อนที่ของลูกสูบถูกป่ะใช่ไหม
ครับ
นะ peak velocity ก็คือ dp by dt เป็นเท่าไหร่velocity ถูกไหมใช่ไหมแล้ว dv เทียบกับ crank angle ถ้าสูงสุดมันจะต้องเป็นเท่าไหร่ dv เทียบกับ crank angle ความเร็วเพราะคุณมีระยะทางการเคลื่อนที่ของลูกสูบที่เป็นฟังก์ชันของ crank angle ใช่ไหมถูกต้องใช่ป่ะแล้วถ้าคุณเอาระยะทางนั้นดิฟเทียบกับเวลานะคุณได้ความเร็วที่เป็นฟังก์ชันของ crank angle ถูกไหมใช่ป่ะแล้วถ้าคุณดิฟอีกครั้งหนึ่งให้มันเท่ากับ0มันจะเป็นความเร็วสูงสุดหรือเปล่า
ใช่ครับ
แล้วหาได้ไหมล่ะ
ก็คือดิฟเทียบเวลา2 ครั้งใช่ไหมครับ
ใช่แล้วไม่ครั้งที่2ต้องดิฟเทียบกับอะไรไม่ได้เทียบกับเวลาสิเพราะคุณจะหาแม็กซิมัมที่ตำแหน่ง crank angle คุณได้ความเร็วในฟังก์ชันของซีตาถูกป่ะ
ครับ
เพราะฉะนั้นถ้าคุณจะหาความเร็วสูงสุดเทียบกับซีตาคุณก็ต้องดิฟความเร็วนั้นเทียบกับอะไรแล้ว
ซีตา
ใช่ถูกไหมเพราะคุณไปดิฟเทียบกับเวลาคุณก็ได้ความเร่งสิ
ก็คือดิฟเทียบเวลาครั้งแรกให้ได้ความเร็วใช่ไหมครับ
ใช่
แล้วก็ดิฟเทียบที่ใต้ทีนึงเพื่อให้ได้
ใช่ถูกต้องคอมมอนมากเลยเรียนแคลคูลัสมาแล้วนี่ใช่ไหมใช่ป่ะ
โอเคครับขอบคุณครับอาจารย์
นะครับโอ้นี่ความรู้เก่าเลยนะเนี่ยอย่าลืมนะพวกความรู้คณิตศาสตร์เนี่ยเอนจิเนียร์เราต้องอยู่กับแคลคูลัสนะโอเคมีคำถามอะไรไหมครับมีไหมโอเคไหมมีไหมครับถ้าไม่มีนะครับก็ขอปิดการบรรยายนะ I will close down my lecture for today okay so see you next week if there is no any questions มีบางคนออกไปก่อนแล้วนี่โอเคครับสวัสดีครับบ๊ายบาย